Alright guys, this will be a little bit longer video today, but this is an example of air resistance. It says an object of mass m is dropped from rest. The force of air resistance the object experiences is equal to a constant c times the velocity of the object. Part A says draw a free body diagram for the object. So for part A, if I have the object, the forces acting on the object are going to be gravity, which is mg, and they are going to be drag, which is equal to CV. Now, a note here, drag is listed as minus CV. This is the direction. And this is the magnitude. Now, on our free body diagram, the object is going down, so that is positive, therefore gravity is positive, and drag is negative. Part B says, what is the object's acceleration in terms of m, c, v, and g? So for part B, we will apply Newton's second law. F net equals ma. We've already put our signs on our forces, so we have mg minus cv equals ma. So A is going to be g minus c over mv. Part C says find an expression for the object's velocity as a function of time. So I will start part C here. So beginning with my expression for acceleration from part B, I will rewrite acceleration as a differential as dv dt. From there, I will separate variables. In doing so, guys, I want you to notice that here is v, and this entire term is connected together due to the minus sign here. Therefore, when I separate variables, i.e. get the v stuff with dv, that whole term needs to go under dv, and dt will be left by itself. So we have dv over g minus c over m v equals dt. From there, I will integrate. Now, some things to note. We were told in the problem at t equals 0, v is 0, and we are asked to find some v of t. So at t, v equals v of t. So these are our limits of integration. So I will integrate between 0 and v of t and 0 to t. Now, the left integral is the most difficult. I will use u substitution to make the integral a bit simpler. So I will let u equals g minus c over m v. I will take the derivative of u with respect to v. That is minus c over m. And then I will solve for dv, the thing I'd like to substitute for. dv is going to be minus m over c du. from there, I will also change my limits. Keep in mind, when you change your limits, you are plugging your limits into your u expression. So for example, I will take 0 and plug it in for v and see what that gets, and similarly v of t. So 0 becomes g minus c over m times 0. That gives me just g. And v of t becomes g minus c over m v of t. So these are my new limits of integration here. After u substitution. So let's rewrite our integral. So I have the integral of du over u. The constant in front of du was minus m over c. That comes out. And my limits of integration are between g and g minus c over m v of t. That's equal to the integral of dt between 0 and t. Next, recall that the integral of 1 over x dx is the ln of absolute x plus a constant here, assuming no limits of integration. In our case, we have limits, so we will just have ln of absolute x, but this is a rule of integration that if you don't have in your notes is useful to remember. Now, I get minus m over c ln absolute u evaluated from g to g minus c over m v of t, and that equals t evaluated from 0 to t. So we have then minus m over c ln of absolute g minus c over m v of t minus ln absolute g, and that is equal to t. I will move the m over c over, and recall, guys, prior to me doing that, that if I have ln of a minus ln of b, that's the same as ln of a over b. Another useful fact here. So I will move m over c over, and I will rewrite my log terms. So I have ln of absolute g minus c over m v of t over g equals minus ct over m. From there, I'll take e of both sides, so I get g minus c over m v of t divided by g equals e to the minus ct over m. From there, guys, we need to isolate v of t. So we have g minus c over m v of t equals g e to the minus ct over m. So we get c over m v of t is equal to g minus g e to the minus ct over m. So v of t is going to be mg over c times 1 minus e to the minus ct over m. Something useful to note, guys, is that this term here is terminal velocity. Okay, so this is the answer to velocity as a function of time. Let's see what the next portion is. Part C says find an expression for velocity. Part D says find an expression for object's acceleration as a function of time. All right. This is part D. So A is equal to dv dt, which is going to be d dt of mg over c minus mg over c e to the minus ct over m. In taking that derivative, let's be careful here. The first term here, that is a constant, derivative of a constant is 0 minus the second term. We have an exponential raised to some power, so we need to do chain rule there. So we get mg over c e to the minus ct over m times the derivative of minus ct over m. So that is minus mg over c e to the minus ct over m times minus c over m. Being very careful, let's cancel out some things. Mass will cancel, c will cancel, and my negative will cancel. So I get then A of t is equal to g e to the minus ct over m. From there, I need to find position. So I need to find x of t. So I know v of t is equal to dx dt. So I have an expression for v of t. It is mg over c minus mg over c e to the minus ct over m. And that is equal to dx dt. So we have dx equal to mg over c minus mg over c e to the minus ct over m dt. We will integrate here. I'm going to assume that the initial position of the object is 0, goes to some final position x, and initial time is t equals 0, and it goes to some final time t. So, beginning with the right integral, since it is the most difficult, I will break that up into two separate integrals. Integral from 0 to t of mg over c dt minus integral from 0 to t of mg over c e to the minus ct over m dt. I will begin with this integral. As it's the most difficult, I will need to use u substitution. So if I let u equal minus ct over m, du dt is minus c over m. So dt is going to be minus m over c du, and my limits, 0 when I evaluate it stays 0, and the t becomes minus ct over m. If I rewrite that integral, so I'll bring the simpler integral I haven't done yet over minus, and then let's rewrite this integral. So we have minus m over c integral from 0 to minus ct over m, and then we are integrating mg over c e to the u du. Let's be extremely careful, guys, and make sure that we don't mess up. In evaluating the first integral, guys, I get mg over c evaluated between 0 to t, and there is a t here, mg over c times t. This negative cancels this one, so we have an m squared g over c squared, and the integral of e to the u is just e to the u, evaluated between 0 and minus ct over m. Alright, and then if I bring the very top integral down, which is this one, that was integral of dx is just x, like so. Alright, so I need to be very careful here. When I plug in mg over c and evaluate t between t and 0, and then we have plus m squared g over c squared, and we have an e to the minus ct over m minus e to the 0 is just 1. So clean this up. That is mg over c times t plus m squared g over c squared e to the minus ct over m minus 1, like so. Okay. Alright guys, all we have left to do is make our graphs. So here's position as a function of time, velocity as a function of time, and we will do acceleration as a function of time here. All right, let's start with velocity as a function of time. So that was mg over c times 1 minus e to the minus ct over m Now, if we evaluate this expression at 0, we get v is 0. And if we evaluate it at infinity, v is v terminal, which is mg over c. So what we have here then is an initial velocity of 0, a final velocity of mg over c. Because we don't reach that until infinity, that is an asymptote. And we have this guy right here. Okay? Now, for acceleration, our expression for acceleration is g e to the minus ct over m. Same trick. If we evaluate it at t equals 0, a equals g. And if we evaluate it at t equals infinity, a equals 0. So we have g here, and we have 0 here. 0 occurs at infinity, so that is the asymptote. So we get this guy like so. For position, guys, we have this very nasty expression here to graph. More easily way of thinking about it is, if we look at velocity as a function of time and we know we need to take area to get position, if you notice between a 0 and a large percentage of v terminal, so what I'm referring to is this portion of the graph here, the area increases rapidly, and then the increase in area from here to here is relatively constant. So we have area increase here, we have area approximately constant here. Okay, so what that is going to correspond to is something that looks like this, and then something that continues off roughly linear like so. I hope this is helpful, guys. Thanks and have a great day.